Building the bot. The prerequisites required to build a bot are that one would need hands-on knowledge of scikit library and NLTK library, which is assumed when you start building a chatbot. Downloading and installing NLTK. We first install the NLTK library by running the pip command and installing the NLTK library. We test the installations by running the Python, then typing import NLTK. Installing the NLTK packages. To install the NLTK packages, we import NLTK and run NLTK download function. This will open the NLTK downloader from where you can choose the corpora and the models to download. You can also choose to download all the packages at once. Text reprocessing with NLTK. The main issue with text data is that it is all in the text format, that is, it's in the form of strings. However, machine learning algorithms need some sort of numeric feature vector to perform the task. So before we start with any NLP project, we need to pre-process it to make it ideal for our work. The basic text pre-processing includes converting the entire text into uppercase or lowercase so that the algorithm does not treat the same words in different cases as different. It's not a rule as such, but we usually convert the entire text into lowercase. Tokenization. Tokenization is just the term used to describe the process of converting normal text strings into a list of tokens, that is, words that we want. A sentence tokenizer can be used to find the list of sentences, and a word tokenizer can be used to find the list of words in a string. The NLTK data package includes a pre-trained punct tokenizer for English, which can be used for removing noise, that is, everything that isn't in a standard number or letter. Removing stop words. Sometimes some extremely common words that appear to be of little value in helping select documents that match a user's need are excluded from the vocabulary entirely. These words are called stop words. The removing of stop words will not alter the meaning of the string. Stemming. Stemming is the process of reducing inflected or sometimes derived words to their stem, base, or root form, generally a written word form. For example, if we were to stem the following words: stems, stemming, stemmed, stemmatization, the result would be a single word, stem. Lemmatization. A slight variant of stemming is the lemmatization. The major difference between these is that stemming can often create a non-existential word, whereas lemmas are actual words. So your root system or root stem of a string, meaning the word you end up with, is not something you can look up in a dictionary, but you can look up a lemma. Example of lemmatization are that run is a base form for the word like running or ran. The word better and good are in the same lemma, so they are considered the same. But if better and good were used via the stemming, better and good would not belong to the same category. Bag of words. After the initial pre-processing phase, we need to transform the text into meaningful vectors or array of numbers. The bag of words is a representation of text that describes the occurrence of words within a document. It involves two things: a vocabulary of known words and a measure of presence of the known words. Why is it called a bag of words? We have been hearing bag of words since the very beginning, but why is it called so? It is because any information about the order or structure of words in the document is discarded, and the model is only concerned with whether the known words occur in the document, not where they occur in the document. The intuition behind the bag of words is that documents are similar if they have identical content. Also, we can learn something about the meaning of the document from its content alone. When we are filling a bag with, for example, coins, we do not place the coin in particular positions within a bag. We might place it on the table, but we do not place it as such in a bag. Hence, all the coins are dumped into the bag, and hence the term bag of words, where the words are dumped into it irrespective of the order. For example, if our dictionary contains the words learning is the not great, and we want to vectorize text learning is great, we would have the following vectors: 1, 1, 0, 0, 1. So the first, second, and the fifth word is present in the bag of words and hence can be extracted out. The TF-IDF approach. A problem with the bag of words approach is that highly frequently occurring words start to dominate in the document. Now, if we can have a bag of coins with 1 rupee, 2 rupee, and 5 rupee coins, and if most of the bag contains 1 rupee coins, let's say we have 71 rupee coins, 22 rupee coins, and 10 5 rupee coins, it is more likely that when you put your hand into the bag and remove a coin, it is 1 rupee coin. Hence, the 1 rupee coin dominates all the other coins in the bag. A similar scenario occurs with the bag of words, where certain words which are highly frequent, dominate the document and have larger score, but may not contain as much informational content. Also, it will give more weightage to longer documents than shorter documents. One approach is to rescale the frequency of words by how often they appear in all documents so that the scores for frequent words like the that are also frequent across all documents are penalized. This approach to scoring is called term frequency inverse document frequency or TF-IDF for short, where term frequency is a score of the frequency of the word in the current document. It can be calculated as the number of times term T appears in a document divided by the number of terms in the document. Inverse document frequency is a score of how rare the across words are across the document. The IDF can be calculated by the formula 1 plus log capital N by small n, where the capital N or the uppercase N is the number of documents and the lowercase n is the number of documents a term T has appeared in. TF-IDF weight is a weight often used in information retrieval and text mining. This weight is a statistical measure used to evaluate how important a word is to a document in a collection or corpus. Let us consider an example. Consider a document containing 100 words, wherein the word phone appears 5 times. The term frequency, that is TF, the term frequency for phone is 5 by 100, which is 0.05. Now assume that we have 10 million documents and the word phone appears in 1000 of these. Then the inverse document frequency, that is IDF, is calculated as log of 10 million by 1000, that is 4. Thus, the term frequency inverse document frequency weight is the product of these quantities, that is 0.05 into 4, which is zero point 0.2. TF-IDF can be implemented in scikit-learn as from sklearn.featureExtraction.text import TF-IDF vectorizer. In the example above, point 2 refers to the percentage of word phone in the documents. So 20% of the words or every fifth word in the document is the word phone. We now have the cosine similarity. TF-IDF is a transformation applied to texts to get two real valued vectors in vector space. We can then obtain the cosine similarity of any pair of vectors by taking their dot product and then dividing that by the product of their norms. That yields the cosine of the angle between the vectors. Cosine similarity is a measure of the similarity between two non-zero vectors. Using the following formula, we can find out the similarity between any two documents D1 and D2. Cosine similarity of the given input strings or non-zero vectors that are D1 and D2, we find the dot product divided by the product of their normals, and this is the cosine similarity. The D1 and D2 stand for the two non-zero vectors.